I don't know if this is how.
I don't know what estás en directo means. Probably means you failed.
No, it says one person is watching, but I can't really tell.
Oh, okay. You provide the Okay, nice. Congrats on your son. I know it's accepted, but.
We're
Oh,
live,
yeah.
but sorry, ¿me estás viendo? Es que no sé.
Right, yeah, yes, they finally did the time so. So, I mean, it's completely.
Thanks for coming.
Yeah, but it's nice because I've been writing else. Yeah. Yes. Just like, I don't have to.
Everybody, do
Still
that.
in the word. Yeah. Yeah, that's quite. I mean, that's.
Something about this table setup feels so
I was gonna say, I don't know what's.
inefficient in this room right now.
Yeah, I feel like you could fit more chairs if we had less tables, but maybe.
I guess it's tough when you're trying to have a unidirectional kind of audience.
Hello?
You're limited.
Put it on the other screen and it could be wider.
Wasn't it more like a squarish kind of table?
I mean, yeah, the setup's been moved around a lot, but I'm trying to think if they added or took away tables.
Sí, ah, bueno, está bien.
I guess sometimes we have two tables against one
Bueno,
wall.
voy a colgar y voy a preguntarle si me oye.
So
Escribe
I don't know for sure, but
Bueno,
yeah, no, usually.
me escribe si no me oye.
No, I mean, when we have our Monday morning coffee bagels stuff, it's
¿Me estás
it's just
oyendo?
mixed up all around. We've had a lot of changes to that event. We got little mini bagels this year. We need more of them.
¿Me oyen? ¿Me oyen?
¿Está funcionando?
Mhm.
So I don't need to do anything further? It's,
No, I think this is it. I think I'm just gonna.
oops, that was my
Have you
nose.
ever imagined you would have a slide with 3 identities on it?
No.
Ever in your
That's my
life?
battery. 90, okay. Oh, no. Mary, do you want to slide down a little bit?
Yeah.
And try to keep accommodated.
Sorry.
No, yeah, you're fine.
Did I not shower this morning?
Yeah, that's all right. I had to like, keep at least a 2.
Having one person in between us is just too few for me. I need to move
Yeah.
further.
So,
I heard you and Troy had a fruitful conversation about paleo-bio topics, about like what defines period boundaries or future stratigraphic.
good for summer.
Common
Well, we
stratigraphic.
did have a long conversation, so.
I like the idea from the short bit.
Yeah, it did.
Yeah, Lex is good.
It's clear.
Cool.
We should
I
try
got it
that
at some point. No, I haven't. I need to.
So, good morning, everyone. And we have quite a week for the Delio program in defenses. And today we're here to learn about the thesis research of Elena Stiles and to celebrate her time here at Penn State and wish her well in her continued journey as a PhD student at the University of Washington very soon. And Elena came to us from the University of the Andes in Bogota. And before coming here, she really had an extensive variety of wonderful field experiences through her several affiliations with the Slovenia Tropical Research Institute and the University of Florida, involving field work in Panama and Colombia especially, and a number of other places in various countries. And let's see, Elena also now has extended her field experience in South America by several thousand miles by joining us a couple of times in Patagonia. And Elena certainly distinguished herself here. She's pulled in, sort of run the table on research grants. I hope I can count on you to advise future students on how to really cash in on those on those awards and competitive workshops and all sorts of things. So without taking away any more of her time, let's turn this over to Elena and let's hear about her work on plant extinction at the KT boundary in southern South America.
So, first of all, thank you all so much for being here this morning. And before I jump into what I have been doing for the last 2 years, I wonder if this is the full laser, I guess not. Before I jump into what I've been doing for the last 2 years, I wanted to acknowledge the co-authors of the manuscript that is this project. So first of all, my advisor, Peter Wolf. Second, Ari Iglesias from the National Institute of Sciences of Argentina, CONICET. Maria Alejandra Gandolfo from Cornell University, and Nestor Rubén Cunio from the Museo Paleontológico Egidio Perugio, our partner institution in Argentina. So, 66 million years ago, a bolide infected the Earth at the Mexican Yucatan Peninsula, leading to the extinction of about 70% of Cretaceous living species and permanently reshaping global ecosystems. Perhaps this extinction is best known for the extinction of the charismatic ammonoids and the non-avian dinosaurs, but the impact on global ecosystems was much more profound. And although we tend to think about this event as a global extinction, there's an increasing amount of evidence that suggests that this extinction may have been globally heterogeneous between northern and southern hemisphere localities. So some examples from the marine and terrestrial paleontological records. Global nanoplankton in the southern hemisphere shows much faster recovery times and almost shows much lower extinction rates and almost immediate recovery times following activity compared to the northern hemisphere counterparts. Pollen and spore records in southern hemisphere localities, although less abundant than those in the northern hemisphere, show that extinction rates were lower and essentially the environmental disturbance felt after the extinction event was shorter lived. And some vertebrate and plant groups that are known only from Mesozoic localities in the northern hemisphere are known in southern hemisphere localities of Argentina and in Australia up until the Oligocene even. So to better understand extinction events on land, we need to look at the paleobotanical record because plants, as a primary producers in terrestrial ecosystems, sustain all other life forms on land by providing mainly food and shelter. So to fully understand the extent and severity of an extinction event on land, it is important to understand the paleobotanical record and all associated information it can provide. Unfortunately, there is currently a large bias in what we know about the KPG paleobotanical record because most of the locality is now concentrated in the northern hemisphere, and actually the vast majority is concentrated in the western interior of North America. Out of the total 107 localities in the southern hemisphere, only 4 are reported, globally, only 4 are reported in the southern hemisphere. And actually, some of the best localities and the most complete resources for understanding this record of KPG and terrestrial ecosystems comes from my study area in Argentine Patagonia. So recent studies from paleobotanical and insect herbivory records from Argentine Patagonia are beginning to show supporting evidence to contrast for this contrasting northern versus southern hemisphere extinction and recovery records. So in Patagonia, we have the best stratigraphically and age-constrained paleontological collections and terrestrial deposits across the KPG, and they are the only comparable material to the very extensively studied North American KPG sections in the western interior of North America. And so far, the evidence that they have provided is that less than 10% of spore and pollen species become extinct across the boundary compared to the 30 to 40% spore and pollen extinction in North America. And I'll just briefly say that when I mean another word for spore and pollen is microfloras. So when you hear microfloras, I'm just talking about spore and pollen records here on out. Insect damage herbivory recovered within 1 to 4 million years after the KPG in Argentina, compared to the 9 million years it took for insect herbivores to recover in North America. And early Paleocene microfloras in Patagonia show much higher diversity than macrofloras for early Paleocenes of the same age in the western interior of North America. However, although the observations of insect herbivory have been made on macrofloras of both pre-KPG and post-KPG assemblages in Patagonia, these collections themselves have not been compared yet, so we did not have a macrofloral extinction rate for Patagonia to compare to the 50 to 60% macrofloral extinction rate observed in North America. So I set out to answer, what effect does the KPG have on macrofloral composition or diversity in Argentine Patagonia using these new pre-KPG and post-KPG macrofloral collections that have not been previously compared? And my initial hypothesis was, well, because there seemed to be a trend of lower extinction rates in Patagonia compared to the western interior of North America, the only real thing I had to go on was the extinction rate that I will find is less than the 50 to 60% that is estimated in the western interior of North America. So the macrofloras that I am studying, in this project, that I studied in this project, come from two collection areas. So for the uppermost Cretaceous, the Maastrichtian stage, we have macrofloras from the Lithic Formation, which have been biostratigraphically constrained to 67 to 66 million years old. And in the early Paleocene, the post-KPG assemblages come from two formations, the Salamanca and Peñas Coloradas formations, that have been dated using a suite of absolute dating and biostratigraphic methods. So we have three localities, and for the Dacian, PL1 and PL2 correspond to Salamanca formation localities, and Las Flores, LF, corresponds to the Peñas Coloradas. So this is early Dacian, so earliest post-KPG, and this is late Dacian, so still within the 3 million year span after the 66 million year boundary. And here, these are magnetostratigraphic terms that are constraining each one of those collections through 3 different time slices. So essentially what I have is 4 different time slices of macrofloral collections spanning 1 slice of pre-KPG Maastrichtian floras and 3 time slices of post-KPG macrofloras, separated by about 400 kilometers along the Paleo-Atlantic coastline. So here is a paleogeographic reconstruction of what this area would have looked like around the time of the KPG. So the macrofloral collections from these localities have so far provided insight into the incredible floral diversity in both Maastrichtian Lithic Formation and in the Dacian Salamanca Formation assemblages from not only vegetative structures, so leaves, branches, twigs, that sort of thing, but also from reproductive structures, seeds, flowers, fruits, and some of them actually have exceptional preservation. These come from a little bit older than the macrofloras that I will be talking about for the rest of the talk, but some of them have cuticle preserved and they have allowed for paleoclimatic reconstructions. And these fossils in the Salamanca Formation never fail to amaze me. They're so beautiful. And actually here you can see within one of the flowers, little pollen grains preserved within. And so far, these are just a few examples of things that have been taxonomically studied. But the vast majority of the diversity in the Maastrichtian Lithic and the Dacian Salamanca Formation still remains undescribed and unexplored in the leaves. And insect damage recovery, extinction and recovery records have been based on observations on angiosperm dicot leaf assemblages, but the leaves themselves have not been compared in search of a macrofloral extinction rate. So this is essentially the focus of my research. Using these huge Maastrichtian pre-KPG and post-Dacian post-KPG dicot leaf assemblages, I wanted to estimate the macrofloral extinction rate and observe trends in extinction and recovery in Patagonian floras at this time. So for the Maastrichtian, the 66 to 67-year-old interval, I should say that all of these studies are based on, all of these analyses are based on, so my study is based on the morphotypical classification of angiosperm leaves. So what this means is essentially taking these collections and creating artificial species based on their morphological characteristics. And these are called morphotypes. So these analyses that I will be presenting are based basically on the morphotypical classification of these angiosperm leaves. So for the Maastrichtian, we have 60 different morphotypes from 926 different leaf fossils. And in the Danian, as I mentioned, we have 3 time slices, PL1, PL2, and LF, including over 3,000 leaf fossils and 49 different morphotypes. So because there is some subjectivity always when creating these morphotypes, okay, maybe I'll just run first through how a morphotype is actually determined. So you take the leaves and you make very detailed observations of their morphology. So what things that you will take into account are overall shape, for example, base shape, apex shape, what the primary venation looks like, if the leaf is lobed or if it's not lobed, what the margin looks like, if it's entire, does it have teeth, what size and shape the teeth are, the secondary venation, does it reach the margin, does it go up to the apex or form little loops, and the tertiary venation, which has its full suite of morphological characters to consider. So because there is some subjectivity always in establishing morphotypical classifications, and the 2 Maastrichtian and the Danian collection morphotyping was led by 2 different working groups, I visited the collection several times to ensure that I was being consistent with what I was considering a morphotype, both in the Maastrichtian and in the Danian. So over the past 2 years, I visited the collection 3 times. So all these leaf fossils are curated at the Museo Paleontológico Virgilio Perugillo in Trelew, Argentina. And I just spent a lot of time just looking through all the leaf fossils, understanding their morphological variation, and what is considered a morphotype, and how much how much morphological variation I'm willing to accept within a single morphotype, what I need to consider new morphotypes. And here I'm actually surely debating very heatedly with one of our co-authors what should be considered a morphotype and what shouldn't be considered a morphotype. So using these huge leaf collections classified into morphotypes, I took a 3-step approach to understanding and exploring the macrofloral turnover across the KPG and Argentine Patagonia. So in the first step, I performed a detailed morphological comparison of all the Maastrichtian and all the Danian morphotypes. So essentially, I was looking for survivor pairs and things that could be considered equivalent species. So I should mention that because there's a wealth of morphological information in leaves, we think that they could be considered to be produced by a single species. So a leaf morphotype is approximately the species equivalent. So I was comparing these leaf collections in search of survivor species. The second, and then I estimated rarefied species diversity for both the Maastrichtian and the Danian collections. So rarefied species diversity is, imagine if you put all the morphotypes into a bag, and then you started pulling out morphotypes, all the specimens actually classified into morphotypes, and you're pulling out specimens and you're documenting how many morphotypes you are sampling, and eventually you're gonna reach a point where you're not pulling out anything new, and this is when rarefied species curves are telling you that you've sampled all the diversity. So basically, a rarefied species curve is a way to estimate how much of the diversity you have sampled and how much is left to sample based on the specimens that you have collected. So I estimated both of those things for the Maastrichtian and the Danian collections. The second step in my analysis was performing a morphospace analysis of all the Maastrichtian and all the Danian morphotypes in the macrofloral assemblages. So this was just a way I used to summarize all the morphological information without taking into account the taxonomic affinities of these leaves, which are still largely unresolved, and to see if there is any change in the overall morphologies of leaves both before and after the boundary, because leaves themselves have, leaf morphology in itself has some relations to environmental parameters. And third, I compared published fallen records in the Lefifan and Salamanca formations to test for geographic heterogeneity. So if you remember, I mentioned that the Maastrichtian and the Danian collection areas are separated by about 400 kilometers along the Paleo-Atlantic coastline. And spore and pollen records are very useful because they are produced in vast numbers by plants, so they're easily dispersed by wind and by water. So they can provide a regional signature of flow composition, and very high stratigraphic resolution. However, well, not however. On the other hand, macrofloras, which is what I'm comparing, are very limited in the stratigraphic ranges. You will usually have an assemblage that is maybe recording a year or something like that of deposition. And so you have less stratigraphic resolution, but higher taxonomic resolution because leaves have much more morphological characters that you can use to classify down into a species essentially. So pollen records will give you composition in terms of higher taxonomic levels, families, or genera in the best case scenario of plants present, of plant families present in those two localities. And I wanted to see if that geographic separation was playing a role in the macrofloral composition that I was observing. It was shifting in DNA assemblages. So the first step of my 3-step analysis, I compared all the 16 restricted morphotypes to the 49 Danian morphotypes in search of survivor pairs based on the morphological characters and architectural characters established in the Manual of Leaf Architecture. This is another way that I was ensuring consistency in the comparison of the morphotypes and the establishment of morphotypes, just carefully following the Manual of Leaf Architecture. And what I found is a 92% macrofloral extinction rate. So this means that out of the 60 morphotypes, only 5 of the 60 restricted morphotypes, only 5 are found in the Danian collections. So now I'm just going to run through those with you. So this is survivor pair number 1. And what I want you to notice here is the curved primary vein. And you can see that the 2 secondary veins here sort of give it a little twist. You can see that it's 3-lobed, or well, maybe you can't because the preservation is not great, but take my word, it's 3-lobed. And this one is also 3-lobed here. You have secondary veins being longer towards the base of the leaf and becoming more loopy towards the apex of each one of the lobes, as you can see both in this one and this one. And in the tertiary venation, this is called a type of tertiary venation called preferent, in which you see that tertiary is coming from both sides, joined towards the middle, forming a sort of ladder-like structure. And in the Danian, interesting, you not only have 3-lobed forms, but you can also have 5-lobed forms. Survivor pair number 2. So here, what I want you to see is the very strong primary vein that has 2 very strong secondaries at the base. All secondaries branch when reaching the apex. So the little branch here is going to irrigate this sinus. So the sinus is just the space between one tooth and the other. And you can see here that this little branch is irrigating the sinus of the overlying tooth. And opposite to sub-opposite secondaries and compound little lobes. Survivor pair number 3. So this is a very morphologically diverse morphotype because they are little leaflets on a compound leaf. But what I want you to see here is that both all the morphological diversity is represented both in the restricted and in the Danian morphotypes. So here you have the curved primary vein, overall ovate shape, so it's wider at the base than compared to the top, wider at the base. You have a mix of secondaries that reach the margin sometimes, and sometimes will loop before reaching the actual margin. Very, very small teeth that have very long sinuses, so again, the space between the teeth. Long and shallow sinuses that are curved, and sometimes you can have an asymmetrical base. There's a little torn up here, but asymmetrical bases in both pieces. Survivor pair number 4. So the preservation here is not the best, but I hope that you can see that the secondaries are straight and are opposite. Straight and opposite secondaries. You have mainly a 3-lobe structure with 2 smaller accessory lobes towards the base. So again, 3 lobes and 2 smaller accessory base lobes. And again, there's consistency in the tertiary venation. So you have this ladder-like structure formed by the preferent tertiaries in both cases. And although the preservation is not enough to show this very clearly in a picture, both of them have tooth margins. And survivor pair number 5, we have looping secondaries. Okay, overall ovate shape, entire margin. Looping secondaries, this is called for the germ explanation. When the secondaries sort of form loops before reaching the margin, you can see that in both the Maastrichtian and the Danian leaves. Some opposite secondaries. So there's just about opposing each other. But a 92 macrofloral extinction rate in Patagonia, if you remember back to the 50 to 60% estimated in North America, seems like an overestimation. So one of the possible sources of bias that we considered was that we only have one stratigraphic horizon that we're sampling. So we're comparing one stratigraphic assemblage in the Maastrichtian to several stratigraphic assemblages in the Danian. And in North America, you have such a wealth of macrofloral deposits that you can actually bin them. You have like meter bins in which you collect in which you can collect macroflora. So there's collections for many different stratigraphic meters leading up to the boundary. So what I did here is I took that data from North America and I binned it into 10-meter groups, and I calculated the extinction rate for each one of the 10-meter bin intervals to see if we had, for example, taken only been able to sample 50 to 60 meters, what would that extinction rate be? Because that's the case that we have in Patagonia. We only have one stratigraphic horizon, and we don't really know if this proportion could change if you increase or decrease the distance from the boundary itself. So what you can see here is that there's an overall trend of decreasing survivorship rate as you go further and further away from the boundary. But even when you're relatively close to the boundary, say if you had only sampled a 30 to 20 meter interval, you would have an extinction rate of over 90%, which is the case in Patagonia. But it's not necessarily the 50 to 60% survivorship rate overall in the Maastrichtian and Danian assemblages in North America. So because we only have one stratigraphic horizon in Argentina, this could be the case that we're observing, and this could lead to an overestimation of macrofloral extinction. But until we have many more stratigraphic horizons sampled, we can't really know if that's the case. But that's just a possible explanation. So for rarefied species diversity, here I'm showing you the rarefied species curve. So again, when the curve sort of becomes flat is when you sampled all the diversity in an assemblage. In the solid lines, I'm showing you sites from Argentina, and in the dashed lines, I'm showing you sites from North America. So here is in black Maastrichtian assemblages, the Liffey Pine Formation, and here the stratigraphic interval 15 meters below the KPG boundary in North America. And here in the Danian, we have the PL1, PL2, and LF localities in Argentina, Patagonia, compared to a 38 meter over the boundary and 7 meters over the boundary assemblages in North America. So the first thing that I want you to see is that there's a drop in rarefied species diversity between the Maastrichtian and the Danian of almost 40%. So this means that, okay, so this is consistent with what is observed in North America, in which you also have a severe drop in diversity across the KPG boundary. So this means that the drop in diversity that I'm observing is consistent with an extinction event. But the second thing that I want you to see is that rarefied species diversity in the Maastrichtian and in the Danian and Patagonia is much richer than species diversity both in the Maastrichtian and in the Danian of North America. So previously, authors had thought that the low extinction rates and the high diversity in South America was perhaps a product of the low extinction rates suffered across the KPG boundary in the southern hemisphere localities. But what I'm showing you here is that there's actually much higher floral diversity even before the KPG boundary. So there is a longer history of floral diversity in South America that needs to be further explored. So moving on to morphospace analysis of Maastrichtian and Danian macrofloral assemblages. So I thought that this was an interesting way to, first of all, ignore all the taxonomic affinities of the leaves that I was looking at because they're mostly unresolved. But by summarizing all the morphological information that you have in these assemblages, you can simultaneously test if there is a morphological turnover in overall morphologies characterizing Maastrichtian and Danian leaf assemblages. And what this means across the boundary is there a selective character loss with just things with certain morphologies fare better than others in the aftermath of the extinction event. So again, I went back to very detailed observations of all the morphological characters of each one of the leaf morphotypes, and I coded them all into a matrix. So the total number of characters I used was 46, and I coded them all into a matrix as discrete characters. So what this means is, say a leaf had an entire margin and a leaf had a tooth margin. So the entire margin would be coded as a number 1, and the tooth margin would be coded as a number 2. And that's essentially how all 46 characters were coded. And these included, again, base shape, apex shape, overall shape, symmetry, basal symmetry, medial symmetry, primary, secondary, and tertiary venation characters, and also what as many characters as I could describing the margin. And what I did with this huge matrix is I ran it through a principal coordinates analysis. So this is an ordination method that takes each one of those axes. So each one of those discrete characters would become an axis in itself. And you take all of those, all that morphological information and compress it into fewer axes that attempt to summarize all the most of the morphological variation that you can see in these leaf assemblages and plot them in a graphical space where you can see the differences between them as graphical distances. So the main result for this part of the study is that there's actually an expansion in occupied morphospace across the KPG boundary. So what I mean by morphospace is the area occupied by all the morphotypes in the Danian or all the morphotypes in the Maastrichtian. So what I see in my results, and it's surprisingly, is that there is much higher morphological diversity in the Danian, therefore they occupy a larger area of morphospace, which is not really what I expected to see when I see a drop in rarefied species diversity and much lower number of morphotypes in the Danian compared to the Maastrichtian. But here you can see, yeah. So also what was interesting is that this expansion in morphospace in Danian assemblages was primarily led by an increase in lobed and toothed leaf morphotypes, things that were not very common in Maastrichtian assemblages. And another interesting, not very significant pattern, but it was interesting, is that leaves in the Danian, so leaves in post-KPG assemblages, tend to have stronger secondary veins reaching all the way to the margin and a higher prevalence of this combination of secondaries reaching the margin and to the margins. And all of those things combined in lobed leaf morphotypes, whereas Maastrichtian morphotypes are more characterized by being entire, relatively simple leaves with secondaries that loop before reaching the margin. So the increase in both tooth and lobed leaf morphotypes was interesting in itself because both of these characters have been associated to environmental parameters in modern leaf assemblage studies. So both an increase in lobed and tooth margins is consistent with the climatic cooling observed between the Danian and the Maastrichtian leaf assemblages. So here I calculated out the percentage of lobed and tooth morphotypes for each of the Vipan, PL1, PL2, and Aspergillus assemblages. And what I want to show and highlight here is that you have a very dramatic increase in lobed and tooth margin morphotypes, but that this proportion remains stable for the 3 million years sampled by these leaf assemblages. And using leaf margin analysis, which is a set of equations in which you plug in just the percentage of tooth margin leaves that you have in an assemblage, you plug that into an equation and it gives you a temperature. But I didn't want to give you the temperature measure per se, but I did want to say that, forget all that. So basically using those equations, I estimate a relative cooling of 5 degrees C between the Maastrichtian and the Danian leaf assemblages. An interesting contrast with North American floras is that many authors studying Western and Interior North America assemblages have characterized uppermost Cretaceous Maastrichtian assemblages as having a particular Cretaceous look in which there's a lot of lobed leaves. So a very loby Cretaceous look in the Maastrichtian of North America. And then you have a sharp decrease in loby Cretaceous look morphotypes across the KPG in North America, which is actually the opposite of what we see in Patagonia. We have very few leaf morphotypes that are lobed in the Maastrichtian, and then you sort of acquire this loby look, Cretaceous North American look in the Danian assemblages of Patagonia. So that's an interesting contrast. So finally, the third step of my three-step comparison, the third comparison of the published foreign scholar records, this also had a two-step process in itself, kind of. So first, I took the published spore and pollen lists of the Maastrichtian and the Liffey-Fan formation, of the Liffey-Fan and the Salamanca formations, and I should mention now that even though the macrofloras that I'm using in this study come from the Maastrichtian strata of the Liffey-Fan formation, the Liffey-Fan formation actually is Maastrichtian and Danian in age. It spans the boundary, but there's no macrofloras preserved in the post-KPG strata of this formation. But there is, however, pollen records, which makes it really useful because then it can test the geographic heterogeneity both in time and across space with the Danian Salamanca formations. And these pollen records come from either the same general collection areas of the macrofloras or from very proximal collection areas. So I compiled all the spore and pollen records, and I limited my comparisons to only species ID level identification. Species level identifications, because there were a lot of cases where you have, pine spores morphotype A and pine spores morphotype B in the other assemblage, and there's no real way of telling what those two different working groups meant. So I just limited my comparison to species level ID. Then after comparing and pulling out all the species that were shared between the Maastrichtian and Danian Liffey-Fan and the Danian Salamanca strata, I compiled a matrix of presence-absence data for all those species level IDs. And what I did is that use a method that I thought was quite interesting called Beal smoothing. So Beal smoothing is a method that is going to help you reduce the noise of uneven sampling for ecological studies. So you will have a list of species and a list of samples. So you have a list of samples and the species present in each sample, and there is a possibility that even though a species was present in a sample, you didn't really sample it and you're not observing it. So what this method does is take that presence-absence matrix and turn it into a probability matrix, which gives you the probability that each species will be present in a sample, even though they weren't present in the sample to begin with, based on occurrences and co-occurrences of that species with other species in other samples. So I thought it was an interesting way to test to see if there was some noise that could be reduced by using this method and giving us more reliable comparisons of species level assemblages. And then I took those Beal smoothed results and plotted them in little clusters to see how similar or dissimilar those assemblages actually were. So first, in the first sort of step of this step, I found that 60% of species found in the Danian Salamanca formation are also found in the Maastrichtian strata of the Liffey-Fan formation. So this means that even across the boundary and the 400 kilometers separating the Maastrichtian Liffey-Fan and the Danian Salamanca strata, you still have 60% shared species of spore and pollen records. And when you compare only the Danian strata of the Liffey-Fan and the Danian strata of the Salamanca formation, this percentage actually goes further up to 75% and includes several spore and pollen taxa that are Danian markers in the region. And even though there's a very high shared percentage of species between the Lifipan and the Salamanca formations, it was interesting to see that in cluster analysis, the separation between formations was actually quite strong, even stronger than when comparing Maastrichtian Lifipan to Danian Lifipan. There's a very strong separation between the two collection areas of the Lifipan and the Salamanca formations. So this means that even though we do have a high percentage of shared species, the associations that these species appeared in the samples could be different, and this could be a product of the geographic separation between the two collection areas. But what was interesting is that the smallest differences observed between the Lifipan and the Salamanca, so the smallest distance separating these two clusters, appears when you're considering only angiosperm taxa, which is what I'm comparing in my macrofloral assemblages. So this means that the lowest heterogeneity between the assemblages is found in the composition of higher taxa of angiosperm families or genera as represented by the spore and pollen species, which I remind you don't have the same taxonomic resolution as macroflorals do. So just to summarize, the 60 and 75% of shared species between the Maastrichtian and the Danian Salamanca and Lifipan formations shows that there is persistent of the same plant families, largely, present in these two collection areas and across time. So just to bring this all together, there is evidence for both from both the macrofloral taxonomical descriptions and the pollen records that suggest that the same families and the same families are present, the same plant families are present in both the Maastrichtian Lifipan and the Danian Salamanca formations. So this is giving us some validation for the comparison of the macrofloral assemblages. Even though they're separated in space, we can confidently say that these assemblages are characterized, well, are made up of the same major plant families. So the main conclusions of my three-step macrofloral exploration of Cretaceous and Paleogene floras in Argentine Patagonia. The macrofloral comparisons indicate a high species level turnover. So because the macrofloras have a much higher taxonomic resolution than the spore and pollen records, it's considered that a high macrofloral extinction rate is equable, the same as a high species level turnover between the Maastrichtian and the Danian assemblages in Argentine Patagonia. The drop in verified species diversity across the KPG is consistent with an extinction event, as has also been observed in North American floras. Microfloras, so spore and pollen, and taxonomically studied macrofloras from the same localities from where these leaves come from show that there is persistence of the same major plant families and possibly even genera across the boundary and across the space separating these two formations. And amorphous space analysis shows not only the persistence, but the expansion of new leaf morphologies across the KPG boundary. So essentially, there's no real character loss, and this was not a morphologically selective extinction in any way. So I set out to answer what effects does the KPG have on macrofloral composition or diversity in Argentine Patagonia? And are North American and Patagonian macrofloras different? Does this comparison coincide with the northern versus southern hemisphere heterogeneity and extinction patterns observed in other paleontological and records? So in terms of the macrofloral extinction rates, we have a much higher extinction rate compared to North America, but there are several sources of bias that can be leading to that overestimation in macrofloral extinction rate. Nevertheless, there is high species level turnover both in North America and in Patagonian assemblages. The drop in verified species diversity is also observed in North American floras and is consistent with an extinction event. But what is interesting is that there is much higher species richness in Patagonia, both before and after the boundary. So there's actually an extended history of richness, floral richness in South America, even before the extinction event. Microfloras show much higher extinction rates in North America, 30 to 40%, compared to the less than 10% in Patagonia, suggesting that there is a higher turnover in major plant families present in North America when compared to Patagonia. And morphospace analysis, although there hasn't been a morphospace analysis done for North American floras, I suspect that it's going to be quite different and interesting when comparing to the Patagonian assemblages, because you have this increase in low morphotypes in Patagonia while you lose the Cretaceous lobe look in North American assemblages across the boundary. So overall, the contrast between the North American and the Patagonian leaf assemblages suggests that there is heterogeneity in the heterogeneity in the extinction and recovery patterns observed between there is heterogeneity observed between the North American and Patagonian assemblages. So overall, this is providing us evidence that there is global heterogeneity in the extinction and recovery patterns when comparing northern to southern hemisphere sites globally. And with that, I'd like to thank everyone that has helped me in the development of this project. So again, co-authors, Peter, my advisor, Ari, Alejandra, who went with me, messing up all the collections all the time, and my lab mate, Gabby, Mike, who, by making these very detailed observations on the leaves, compiled these very detailed, extremely organized databases for all the leaf specimens that very much helped me when I visited the collections. Anita and Andres, which hosted me every single time that I went to visit and took me whale watching. And my committee members, Tim and Mark, for all their support and help throughout the development of this project.
Great. Thank you, Elena.
I'm an aggressively emotional person, I'm sorry.
Good exhale for 30 seconds.
Okay, I'll exhale, but I'll also say now that I'm very grateful for all the people that I've met over the past 2 years.
And we're grateful to you for being here for 2 years.
Yeah.
Thank you for coming here.
Okay.
And now the public, like these folks in the room, to represent the public everywhere, I suppose. They ask questions of the candidate.
Yes.
So this is now common, well, it's commonly accepted that there is a difference between recovery patterns between the northern and southern hemisphere. What do you think is a good causal mechanism for that, especially considering, the nanoparticle photosynthesize show similar patterns to the plants?
Mm-hmm.
So what do you think is what do you think explains that?
Okay. Well, there's 3 main hypotheses for why there could be this heterogeneity in extinction patterns between northern and southern hemispheres. So, first of all, southern hemisphere sites have an increased distance from the actual Mexican impact site. So, if you increase the distance, that you'll have less ejecta and possibly a decreased influence of all the toxic gases that were produced in the aftermath. Well, not in the aftermath, in the impact itself. Because oceanic buffering of impact winter temperatures is also something really significant, because in the southern hemisphere you have mostly water, in the northern hemisphere you have mostly land. And when all this dust and ejecta was blown up into the atmosphere, it's estimated that between 10 to 20 degrees of cooling occurred. And when you have the ocean sort of acting as a temperature source, then you buffer those temperature decreases in the southern hemisphere localities compared to the northern hemisphere. And maybe the impact angle, although I know there's hypotheses that it could be different, but one of the hypotheses suggests that the impact led most of the ejecta to blow up into, most of the impact was directed sort of northwards, so most of the ejecta was dispersed in northern hemisphere localities. So in terms of why photosynthesizers do better than other things. I think, especially in the case of plants, they have the possibility of surviving in seed banks because the cooling and the effects of the actual climatic disturbance is not very long. But seed plants, well, plants in general have the capacity of surviving in sort of seed banks and hold on until growing seasons are able to pick up back up again. I don't know if that's the case for photosynthetic nanoplankton. Maybe things can form cysts and hang out until things get better again. But in terms of why plants seem to be doing better than everything else, I think that would be the explanation that they can just wait for a little while.
So we've actually found, just as a follow-up question, that nanoplankton populations at Chicxulub are actually not too dissimilar from distal sites. So like in the Tethyan Ocean. So it seems like distance might not be actually like the controlling factor on the recovery patterns. So could you anticipate, like if you stayed at the same latitude as Argentina, that kind of moved further east, would you expect to maybe see the same percentages there that you see in Argentina or not?
Like macrofloral assemblages. So the floral composition is very different. There are other southern hemisphere sites. So when you go to, I don't know, Antarctica, or when you go to New Zealand, you will have very different compositions because they're sort of mostly independent land masses, although at this time there is some connection. So I don't think I would see the same assemblages. And if I go for
similar extinction rates, recovery rates, like even if you're not seeing the same species, do you think the extinction rates are similar?
in Antarctica, there's actually little evidence that there is an extinction event at all. That might just be because there is stratigraphic bias in the sampling. Maybe they're missing a chunk of essential time in the earliest Paleocene. But I do think that there should be sort of similar extinction rates when comparing New Zealand, for example, and Patagonia.
I only asked because it's actually really interesting in the nanoplankton. Like it actually seems to be more of a longitudinal trend rather than longitudinal trend. So like we have a lot faster recovery of nanoplankton actually in the Pacific Ocean than we do like the Atlantic Ocean. So I think perhaps instead of like the latitudinal that's I asked.
Yes. I don't know.
Is there any evidence in what you looked at that supports that these two sites were built at similar elevations?
Yes, they're both paleocoastal low-lying forests. Yes. Yes, Gabby.
So given those like depositional environments, like I liked how you were like looking at the variety and like the stratigraphic levels of the Hell Creek. But what about like the depositional environment of the Hell Creek? Like how do you think that the two different depositional environments between like the northern hemisphere and your sites would affect like the number of morphotypes that one might collect and like the pollen, where the pollen is preserved to like create those different extinction rates?
So something that is good of Patagonian and Hell Creek assemblages both is that there is a wide range of depositional environments. So mainly they're both channel fills and channel fill deposits, both in the Hell Creek and in Patagonia, and even across different bases changes, both in the Patagonian assemblages and in the Hell Creek, you have similar assemblages. So I think that just a general caveat of macrofloras is that you're capturing a more localized signature, but the persistence of those same assemblages across different species suggests that it was a relatively homogeneous sort of assemblage compared in both ways. Yes, Ben.
You mentioned in the Lefipon that it comprises both Maastrichtian and Danian strata. So is the actual KPG boundary there pinpointed by some lithostratigraphic boundary, or is there geochemical data which helps you pinpoint exactly where that boundary is?
No, the boundary is not there in itself, but based on very dramatic changes in the macrofossil composition of marine invertebrates, it has been constrained to about a 4-meter interval.
Mm.
So you have things like very drastic changes in mollusk compositions. And there's a shell lag layer of turritellid gastropods, which is interpreted to be the earliest Danian depositional layer, but the actual boundary itself is not preserved, and there's no real geochemical evidence for it either there.
Is there any sea level shift associated with this interval, or is it meant to be completely flatline?
No, there's actually like a huge inconformity between the Maastrichtian and the Danian strata.
Mm.
So you have this sea level rise that is observed in all the coastal localities of this time. So that complicates everything. Allison.
So it's interesting because your pollen data seems to support your initial hypothesis, right, of the southern hemisphere sites having lower extinction rate. But then your macrofloral doesn't, and I wonder if it's the different taxonomic level that you're classifying it as. And is that something that, like, in the northern floras and the macroflora and microflora, do the extinction rates differ that drastically too?
Yeah, so not as drastically, but they also have a lot more stratigraphic sampling, and in this case we have that one stratigraphic horizon, so it's complicated to know if you had more horizons how much that extinction rate would differ or not, but in general you will always have higher macrofloral extinction rate compared to the pollen, because macrofloras are species level, sort of species equivalents, and the spore and pollen records are families or genera. And it really takes a lot to kill out an entire family or an entire genus, because you need to get rid of all the members. So that's why in general you will see a much higher extinction rate in the species than in the families or the genera, which is what is represented in microfloras and macrofloras.
So can I just ask a quick
Yeah.
follow-up? So then in the because you showed us the macroflora extinction rate for the northern hemisphere, right, which is what you're at. Then what's the corresponding microflora extinction rate?
30 to 40%.
Okay.
Less compared to the less than 10%.
Okay. Awesome. Thank you.
I guess I'm just curious about the survivors, and like if they tell you anything about what happened, like why did those ones survive, and like I guess with like the leaf margin analysis, like thinking about is that shift because the different leaves were more resilient to whatever the killing mechanism was, or did it actually get colder or warmer? Or something like that?
I think that particular leaf morphology is just better suited for cooler temperatures, but I don't think that any particular leaf morphology helped anything survive better than other things. Because when you look at the morphospace analysis and the leaf morphologies that survive, there's entire margins, tooth margins, not lobed. So there's no real pattern in things that survive in terms of their morphological characteristics.
Just a follow-up question to that. You said that in the early Danian in North America versus South America, the morphology of the leaves are very different. Is that just a function of like the different climates in the two different sites, or do you have any like?
I think it might be more of a phylogenetic, like family composition reason, because that cooling that you observe between the Maastrichtian and the Danian is observed in global records. So you do have that temperature change both in North America and in South America. So I think it might just be more a product of the families that are present. Yes, Claire.
Nothing new
Nothing new.
between the two sites.
What do you mean?
Nothing that you found in the Danian that didn't find in the Maastrichtian.
So like, you mean like in terms of the survivors? Or?
Yeah. Well, yeah.
Well, most of the things that are in the Danian are not in the Maastrichtian and vice versa. That's just the 5 shared species. So if, I guess everything, it's not those 5 morphotypes would be new. But they're not new. Other people have looked at them. And, yeah. I think that what is new is the comparison.
Anyone else? Right? No question? Okay. Okay, thanks for coming, everyone. Take 5 and
Take coffee and munchkins, please.
reserve about 5 minutes. Thanks for coming.
Oh, wait, finally.